Yes, so you can see the screen, right?
Hello.
Advita, you can see the screen?
Yes.
Yes, question 12, right?
Yes, sir.
We did till question 11, now 12.
Yes. Yes. A spacecraft travels from the Earth to the Moon. At a certain point in the journey, it has zero weight. Why is there zero weight at this point? Sir, I think the answer is B. The spacecraft leaves the Earth's gravitational field.
Yes, correct.
I think option A is really confusing.
Which one?
Why would the gravitational fields cancel each other?
No, they are just saying it that if the gravitational field are equal and opposite, and the spacecraft spacecraft is in between, in the middle of that, then it could be. Then it could be.
Oh,
Okay, now 13.
a sphere of mass 80 kilograms accelerates down a slope at 2 meters per second square. The gravitational field strength is 10 newton per kilogram. What is the weight of the sphere and the resulting force on the sphere?
Yes, which one?
This one, the weight is 800 newton and the resulting force, it is C.
Yes. Please see. Then
Number 14, the weight of the cylinder on the moon is less than its weight on the Earth. How do the gravitational field strength and the mass of the cylinder on the moon compare with the values on the Earth? The gravitational field strength is, wait, so it is C.
it is C. Okay. The gravitational field strength on moon C. Less mass on moon same. Yes, correct.
Sir, but I have a question.
Yeah, sure.
So in other instances, if there is any question about the gravitational field strength of moon, so will I write less than Earth or will I write 0?
Gravitational field strength on moon will not be 0.
1.6. So
Gravitational field strength on moon.
close to 0.
Yeah. It will be 0 in the space, not on the moon. Okay.
Okay.
Then structured questions. Yeah.
Water is transported to a village in a tank pulled by a tractor. Figure 1.1 shows a tank being pulled by a tractor. The combined mass of the tractor and the tank is 4,100 kilograms if the tank is empty, and 6,500 kilograms when the tank is full of water. The density of water is 1,000 kilograms per meter cubed. Calculate the volume of the water in the tank when it is full.
Calculate the volume of water in the tank when it is full. So what will be the answer?
I'm calculating. I think the answer is 2.4 meter cube.
So you got the mass. What is the mass?
2,400 kilograms.
How?
6,500 minus 4,100.
So you got the mass of water.
Yes.
That is kg, right?
Yes.
2400 kg. Then your density is given.
Yes, 1,000 kilogram per meter cube.
Okay, 1000. Then you have to
So
find
I
the
divided the mass by the density.
volume equals mass
Mass
by
by
density.
density.
Okay, mass by density. Then it comes 2400 divided by 1000, right?
Yes, 2.4
So it is 2.4. 2.4. What is the unit?
meter cube.
Meter cube. Okay. Yes. Then what is the next question?
A force applied to a solid object may cause it to accelerate so that its velocity changes. A. State two other properties of the object which may change when a force is applied.
Okay. By applying force, what are the two things or properties can be changed?
It can change the shape and volume.
Yes. Then anything else?
Um, so is it
It can
related to the object's volume, mass, and density, or can I write something different?
actually it's
Like it can
you
change
can,
direction of motion and such.
yeah, direction of the better. If you write direction of the object change is better, huh?
So I can write these as well here.
Yeah, direction of the
Oh, I thought the topic is mass, volume, and density, so I have to write only things related to that.
yeah. So you can write that change the motion of the object, change the direction of the object, right?
Direction.
Yeah. Then you can decelerate the object, right? You can
Yes,
stop the
sir.
object. Okay, that one you can bring here because normally we get the change in shape and size in deformation. Later, we will get it later. Okay,
Sir.
so here we just bring the idea which one is related to change in motion. Okay, so change in
Yes, sir.
motion we can have three ways. One is accelerating, another one is
Change in
decelerating.
direction, deceleration.
Yeah, three ways. These three ways.
Yes, sir.
Deceleration,
I learned this
deceleration.
in dynamics.
Finally, deceleration finally it stops, right? So if someone
Yes,
is
sir.
saying that it's stopping the object, that is also okay.
Okay, sir.
The next,
Number B, a spring has a mass of 0.012 kilograms. The gravitational field strength is G is 10 Newton per kilogram. Calculate the weight of the spring.
it's very
So
easy, right?
it's 0.12
Yeah,
newtons.
0.12 newtons. Very good. Then this one.
Number 3, figure 3.1 shows a painter standing on a wooden plank directly above the right-hand support. The plank has a length 3.6 meters, width 0.35 meters, and thickness 0.025 meters. The gravitational field strength G is 10 Newton per kilograms, and the mass of the plank is 23 kilograms. It calculates the density from which the plank is made.
Yeah, calculate the density. Hello?
Yes, sir?
Yes, are you doing? Calculate the density.
Yes.
Alhamdulillah.
Sir, I got 730.15 kilogram per meter cube.
700.
30.15. Oh, sorry, 16.
Okay. 730.16 kilogram per meter.
Kilogram per meter cube.
Okay, so yes, it can be the answer. Yeah, wood's density is like that, isn't it?
Yes, sir.
Because sometimes we see wood are floating on the water, right? and
Yes, sir.
water has a density 1000 kg per meter.
1000 kilogram per meter cube.
So when it is little bit less than water, then it can float, isn't it?
Yes.
This wood is like that.
Yes.
It can float on water, isn't it?
Yes, sir.
Okay, so here we go. We have the worksheet done, isn't it?
Yes,
We are
sir.
done with the worksheet. Now we can do revision work. Okay,
Okay, sir.
whatever we did before, we can do the revision work. We had these four topics. Uh, topic 1, 2, 3, 4 for our final term. This will be in our final term exams. And other topic, turning effect of forces, we will shift it to final term. Okay,
Okay, sir.
that's why we are not starting that one. We are focusing on this four. Okay, now if we are thinking that we are confident, then after one lesson we will, if we want, we can start, right? That one. Uh, okay, or we will continue the revision only because
Sir,
before
I
exam.
think we can start the chapter.
Is it okay for you? We can start.
Yes, sir. Yes.
Okay, okay. If you want, then I can continue the new.
So no
Otherwise, we
problem,
can.
sir.
Okay, so fine. If you agree, then I can go forward. I'm attaching here new one.
Okay, sir.
So this one is related to turning effect of forces. Huh? Turning effect of forces, we understand from our door.
Yes.
In your door, if you are trying to open or close the door, and if your door is attached to the hinges, right, at the corner,
Yes.
so that one is actually working as the pivot, the hinges, right?
Yes.
And when you are turning, you are applying force on the door, right?
Yes.
The distance directly from the hinges straight, where you are applying force, that distance is called perpendicular distance from the pivot.
Okay.
And if your hand is closer to the hinges, then perpendicular distance is less. And if your hand is a bit far away from the hinges, then your perpendicular distance
Perpendicular
is
distance is more.
more. So if the perpendicular distance is more, you will feel that you need little force to move the door.
Yes, sir.
And it is happening due to the product of the force applied and the distance from the pivot. That product is called moment. Okay, so
Okay, sir.
when you are getting longer distance from the pivot, that time your product of force and the distance from the pivot is greater. That's why you are getting greater moment. and this greater moment is helping you to uh, move the door with ease, right?
Yes.
So this uh, effect is called turning effect of forces, and in short, it is called moment. Okay, so
Yes, sir.
this benefit not only we are getting in this door, we are getting in many places in our life. We if you think of the um, pliers, if you are thinking of the scissors, if you are thinking of the uh, you know the to undo the bolts, nuts, we are using the instrument. What is that called?
Um, Forgot.
This one.
Um, I forgot
You
what
forgot.
this is called.
You forgot the name. So here we gave this the example. I forgot. You also forgot. Huh? Maybe after some
Yes.
time it will come to my mind. So this one, you see, if the hand is longer, then the distance from the pivot is more, right?
Yes.
That time we are having greater moment, so we need less force, right? We need less force to
Yes.
undo the nut or bolt. Is it clear? It's called spanner. Spanner.
Yes.
I can
Oh,
remember now.
yes.
I can remember now. It's called spanner, and it is used in all the machineries, right? For repairing,
Yes.
for any types of manufacturing. We are using this, right? Especially the vehicles and big machineries. We have lots of nuts and bolts, right? For the we have different sizes spanners,
Yes.
so we are using this. So here we are having the discussion of turning effect of forces. Okay,
Okay, sir.
and you know about the crowbars, right? You know about the hammers, even
Yes.
hammers. If the hammer
Yes.
is has a longer hand, then you can easily hit anything, right?
Yes.
Okay, so all these are examples of turning effect of forces, moments. So can you please read the learning outcomes?
Learning outcomes. Candidates should be able to describe the moment of a force in terms of its turning effect and relate this to everyday examples, state the principle of moments for a body in equilibrium, define moment of a force and recall and use a formula, moments equal to force into perpendicular distance from the pivot and the principle of moments, describe how to verify the principle of moments, describe how to determine the position of the center of mass of a plane lamina, describe qualitatively the effect of the position of the center of mass on the stability of simple objects.
Yes, so here we are having the turning effect of forces, then principle of moments, then we have here stability, stability of the object, uh, how it is depending on the center of mass of the object.
Okay, sir.
Okay, that one we try to understand little bit, not that much, little bit we try to understand. So here we have some examples of turning effect of forces. Uh, can you please write the heading of today's topic, topic 5, turning effect of forces?
So I've written it.
Then you write the definition of turning effect.
Okay, sir. So I have taken the notes.
Yeah. So here we have some examples of turning effect of forces. Can you read those?
Examples of turning effective force. A person pushing a pushing a swing will make the swing rotate about its pivot. A worker applies a force to a spanner to rotate a nut. A person removes a bottle's cork by pushing down the bottle opener's lever. A force is applied to a doorknob when the door swings open about its hinge. The driver can turn a steering wheel by applying force on its rim.
Okay, so here we got some examples, and other than these examples, we have also seesaw, right? Playground seesaw.
Yes.
That one is also using turning effect. Okay. Then we
Okay.
have seizures. I told. Then pliers, right? All these are examples of turning effect of forces.
Yes.
Then crowbars. They are also using turning effect of forces. And
Yes.
even my laptop's screen. This is also using the turning effect of forces,
Yes.
isn't it? So there are many places we are having this turning effect of forces.
Yes.
So you write examples of turning effect of forces. You do not need to write all these things. Just you write the instrument name. The first one you write playground seesaw, which one is more common to us, right? Then you write scissors, pliers, the staplers. Just hinges of the door, then crowbars. Okay, this way, etc. You will. Then the formula, huh? Moment of a force. Can you read, Adita? Are you done that part? Adita,
Hello.
yes,
Sir, I
Adita.
got disconnected.
Yeah, okay, I understood later.
I
So
have very
you
poor
are back.
internet connection
So
here.
did you write the examples?
No, I couldn't hear anything. Please repeat it.
The examples of turning effect of
The
forces. Did you write?
no, I could not.
Yeah, you just write only the name of the instrument, not all these details. Just write playground seesaw, then staplers, then pliers, okay, scissors, door hinges, this way, okay, spanners, okay,
Okay, sir.
then moment of a force,
Moment of a force. The moment of a force or torque R is defined as the turning effect of the force about a pivot and is the product of the force and the perpendicular distance from the line of action of the force to the pivot.
yeah, so You write the heading moment of a force, then you write the formula. Write the formula R equals F cross D, where F is the force applied and D is the perpendicular distance from the pivot. And the SI unit of moment is Newton meter. Is it done?
1 minute. Yes, I've written
Yeah. Now, this one you can do, right?
it. Yes, sir.
Then what is the weight? Weight of the mass, metal block.
Okay, so at first do I have to find the moment?
Yes. You find R1 and R1 will be equal to R2 because they are balanced, right?
Calculate. So the answer is 4.8 Newton.
4.8
Newton.
newtons, right?
Yes.
Weight of the metal block is Newton. Okay, equilibrium. Balance, right?
Equilibrium. A rigid body is considered, yes, is considered to be in equilibrium if there is translational equilibrium and rotational equilibrium. So what are these two?
Yeah, continue, you'll get it.
Okay. A body in equilibrium experiences no acceleration and will remain in equilibrium indefinitely unless it is disturbed by an external force. Newton's first law. Translation equilibrium. The first condition for equilibrium is that there will be no resultant force. This means the sum of all acting forces is zero. Translation equilibrium is obtained with the resultant force or vector sum of all forces acting upon the rigid body zero. In simple terms, it means that forces pointing to the left equal to forces pointing to the right, and forces pointing up equal to forces pointing down.
Okay, so translational equilibrium is related to force, and your
Yeah.
force upwards, force downwards, force left, force right, all are equal, all are balanced. Okay, that is called translational equilibriums. Is it clear? So, is it clear? Translational equilibrium. Hello? Hello? Translational equilibrium, is it clear to you?
Yes, sir.
Okay. And there is another one, this is rotational equilibrium. Can you read this? Rotational equilibrium.
Rotational equilibrium, principle of moments. Rotational equilibrium is obtained when the algebraic sum of the torques is zero. The sum of the torques must equal zero. What is this after that?
Yeah, you see,
Summation
it's
of?
written,
What
yeah,
is this?
summation of that torque, right? They are saying tau. The symbol is tau for torque. Uh, Actually, this is not that important to know the symbol or the torque. We just know about the moment. Torque is the synonym of moment. So torque, moment, same thing. Yeah.
Okay, sir.
Okay. Then you see it's written there. The sum of the torques must equal to zero. That means you see we have torque in the diagram below. We have torque left side. We have also torque right side. We have
Yes.
the moment left side and right side. You see the right side one is clockwise and left side one is
Yes.
anti-clockwise.
Anticlockwise.
And the clockwise and anti-clockwise moments, if these are equal, that time we see the object is in equilibrium. And this equilibrium is called rotational equilibrium. When moments are equal, clockwise and anti-clockwise moments are equal, this equilibrium is called rotational equilibrium because it's related to turning effect. Okay, and
Okay. So an example of translation equilibrium is like when it happens in tug of war, and an example of rotational equilibrium is like in a seesaw.
yes, 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 correct, correct, excellent. You understood it. So you write both of them. You write from here.
Yes, I'm taking note.
Yeah, translational equilibrium and rotational equilibrium. You write. Then translational equilibrium means the sum of all active forces zero, and you give the example tug of war. That one is very nice example. And you mentioned this one, especially this one. These two bullet points for
Okay, sir.
translational equilibrium. Forces left, forces right are equal. Forces up, forces down are equal. And rotational equilibrium, you write this one. The
Okay.
counterclockwise direction. That means you write simply that clockwise and anti-clockwise moments are equal. That's called rotational equilibrium. Done.
Yes, sir.
So we have here that one you said playground seesaw. We have here rotational equilibrium. Huh? So here you write after your everything is done. You write principle of moments. Huh? Principle of moments. You write the heading, then you write this statement.
Okay, sir.
Are you done with this statement?
I have written.
Yeah.
Yes, sir.
Okay. Then you
So it is
see,
related to rotation.
yeah. So we are done with principle of moment. Now we are going to center of gravity. Huh? Center of gravity. You see, we have then we have stability. Huh?
Yes,
Then we
sir.
are done with this topic. So what is center of gravity? Can you read please?
It is useful in certain calculations to consider an imaginary point in a body of matter where the total mass or weight of the body seems to concentrate. The imaginary point is termed as the center of mass.
Oh, your voice is not clear.
So the center of gravity is the center of mass.
Yeah, your voice is not clear. Amrita, hello, hello. I got hello, Amrita.
Hello. Yes, sir.
Yeah, for the timing, I couldn't hear you. Your voice was not coming clearly.
Sir, I couldn't hear you.
Yeah. So, can you please read it? The definition of center of gravity, center of mass.
The center of mass of a body of matter is an imaginary point at which the entire mass of the body seems to act.
Yeah.
I have a
So
question here.
yeah,
Is center of gravity and center of mass almost the same thing?
yeah. Is in 99% cases it is same. Yeah. In some cases it becomes different in some special conditions, like on our earth in some places there is change in gravitational field, right? And due to change in gravitational field we get sometimes center of
Yes, sir.
gravity is different, a little bit different than center of mass, otherwise it's same. Okay, otherwise it's same. Is it clear?
The center of gravity of a body of matter is an imaginary point at which the entire weight of the body seems to act. When a body is in a uniform gravitational field, the center of gravity is the symmetrical center of the body, especially in symmetrically shaped body composed of homogeneous materials. So, what is homogeneous material?
Homogeneous material means same thing, like you have the all the things similar, that is called homogeneous material.
So, it's like consistent throughout.
Yes, consistent. Yeah.
Okay, sir.
Then you see some conditions are given there for hollow bodies or irregularly shaped objects. The center of gravity or center of mass may occur in space at a point external to the physical material. The center of gravity can lie outside the object. For example, in the center of the tennis ball or between the legs of a chair. The center of a tennis ball, there is empty, right? Space there.
Yes, sir.
So we are having that example that is not on the surface, it's in the inside the place where actually there is no
Okay.
particle available, isn't it?
Yes, sir.
Tennis ball or football, if you think.
Yes.
Yeah,
Yeah, there is nothing inside.
yeah. So that is one exceptional thing. Now, note. Can you please read note?
Yes, sure. Although the term center of gravity is widely used, the same imaginary point in a body may also be called the center of mass. Its weight and mass are proportional in a uniform gravitational field. Because the center of mass does not require a gravitational field, many physicists prefer the term center of mass to center of gravity.
Yes. So,
Example, the center of
example.
mass of a uniform rod is the center of the rod.
Yes.
Okay,
For
I
some
understood this.
common shapes, we have these all are regular shaped, right? These all are regular shaped
Yes.
object. So their center of mass we can identify easily at the center of the object. You see, we have here uh, surface sphere. Sphere we have, then we have cylindrical shaped object, we have rectangular shaped object, and we have equilateral triangle, that's pyramid, right? We can find the center of mass easily.
Okay.
But for irregular shaped object, here we have one shape that is made from hard paper, okay? And you can get the center of mass by doing one experiment. Do you know about this experiment? Hello?
Sir, I read about this somewhere.
Yeah. Do you have any idea about this experiment? How to find the center of mass of irregular shaped object?
We are going to uh, actually first we're going to drill a hole in the pin, which will be held by a clamp, in, and then we are going to align a plumb line with it to find its lamina. After that, we are going to mark a line just behind the plumb line, and then repeat for very different regions. And then where these intersect, that's the center of gravity.
Yeah, that's the center of mass or center of gravity. Yes. So, is the way how to get the center of mass of irregular shaped object. Okay, you should
Okay, sir.
learn the steps, and you should mention in three steps. Okay, the whole process.
Okay, sir.
Then stability. Yeah,
Stability refers to the ability of a body to restore to its original static equilibrium after it has been slightly displaced. Body in equilibrium experiences neither linear acceleration nor turning effect, and unless disturbed by an outside force, will continue in that condition indefinitely.
okay, look here we have this stable, unstable, and neutral equilibrium. And we have some more discussions here. So this part, stability part, we will discuss more details in next class. Okay. Till here
Okay.
today, we are till here to find the center of gravity of irregular shaped object. We are done. Okay. Stability we will continue in next
Okay, sir.
class. Okay. Thank you so much.
Okay, sir.
Allah Hafiz.
Assalamualaikum, sir. Allah Hafiz.